So in this video, we're going to talk about an introduction to limits. And when we talk about limits, I want you to remember two words: approaching and approximating. So what we want to do is we want to approach a specific x value, and we want to approximate what's going on with the y value. When we talk about limits, notation is going to be really important here. We're going to see this kind of notation. And what this says is we want to take the limit as x approaches c of the function f of x. And if it exists, then we're going to get some kind of value here, and we're just going to be generic and call that value L. Now, it turns out that the function may not actually be defined at that value c. Whatever that x value is. That has nothing to do with whether or not the limit exists. And we're going to see some examples of that in just a little bit. So what I want to do is kind of skip around on the notes just a little bit and talk about this idea of a left hand and a right hand limit. So when we start talking about limits, we usually start with graphs and pictures of graphs. And for the limit to exist at a value c, so for limit as x approaches c of f of x to exist, then the left hand and the right hand limits have to exist. And they have to be the same value. So this idea of left and right is going to be really important here. If we're talking about a left-hand limit, we're going to see notation that looks like this. I want you to notice this little negative. That's where the exponent would normally be when we talk about functions and where exponents live. And what that means is that we are taking a left-hand limit. So we're saying as x approaches this value c from the left-hand side, and we're saying it's going to reach some number, we're just going to call it k. We can also talk about a right-hand limit. I'm going to zoom in on the notes here. Notice that plus. That means not that we're dealing with a positive number, but that we're approaching this number c, whatever it is, from the right-hand side. Now, for a limit to exist, the left and the right-hand limits have to match up. So what I want to do is go talk about and look at a few examples where we can see some graphs. So let's look at this. We have a piecewise function here, and we want to talk about what's the behavior as we get close to x equals 0, x equals 1, and x equals 3. So when I'm asking about behavior, I'm really asking about limits. I'm asking what is the limit as x approaches 0 for this particular picture. And I'm just going to call that function f of x since they're calling it f of x here. But before we talk about 0, we really need to talk about and discuss this idea about approaching 0 from the left and approaching 0 from the right. So let's start from the left. So here's our left-hand side, and I want to come in and zero in on x equals 0, which is right here. So I'm going to come along, and I'm just going to kind of draw on the graph. I'm going to follow that graph on the left until I get close to 0. Now see, as I get close to x equals 0, that y value is 0 also. So we're going to say that left-hand limit is approaching 0. Now if I look at the right hand, I'm going to come in from the right, and notice it jumps down here. And as I get close to 0, notice that y value is getting close to 0 also. Since the left hand and the right hand limits are both 0, then we say that limit does exist and that value for that limit is 0. So we can do the same thing at 1, but 1 is going to be a little bit more interesting because we have this jump in the graph. Notice this is not a continuous function. When you talked about the idea of continuous functions in an algebra class, maybe like pre-cal algebra 171, you talked about, could I draw the picture without picking my pencil up? Are there any kind of gaps or holes in the graph? Well, at 0 is continuous, but when we talk about 1, there's this big gap here. So notice this function is not continuous at 1, but let's talk about that behavior in terms of limits. So we want to know what is the limit as x approaches 1 for the function. But to determine that, we need to look at left-hand and right-hand limits. So I want to get close to 1. I'm going to come in from the left, and I'm just going to follow this graph. And as I get close to 1, my y value is getting close to 1 also. So we say that left-hand limit is 1. But when I come in from the right, and remember I'm getting close to 1, my graph stops here from the right, and notice my limit here is going to be 2. So from the left, I'm coming in at 1 to 1. From the right, I'm coming in and getting 2. I'm not getting the same thing here, which means the limit at 1 does not exist. For that limit to exist, the left and right hand limits have to match up, and they're giving us different values. So now let's talk about part C. And this is where you may want to pause the video, try it, and then come back and check your answer. To talk about the behavior as x approaches C, we can talk about the limit. As x approaches 3. But to talk about as x approaches 3, we need to talk about 3 from the left and then 3 from the right. So as I approach 3 from the left, this is my left-hand side, I'm going to follow that graph, and then it jumps here. And notice as I get close to 3, my y value here is going to be 3. 3 from the left. As I come in from the right, my y value is also 3. Because the left and right hand limits are coming in and we're getting the same value from the left and from the right, then we say that limit does exist at 3 and the value is 3. Now we could also talk about what is the value of the function at 3. And if you notice on this graph, we have an open circle here, which means in this case, f of 3 is not defined. So I'm going to say it does not exist because there's not a solid circle anywhere at 3. So notice in this case, even though that function is not defined at 3, the limit still exists at 3. Now that was different than what happened in part A, just revisiting here. We found the limit to be 0, but if I asked you what is f of 0 based on this picture, you would tell me that f of 0 is defined to be 0 because we do have a y value that corresponds to that x value of 0 there. So now let's go back and look at a function that's a little bit more interesting. Let's talk about that f of x is equal to the absolute value of x. We could actually rewrite the absolute value of x in terms of a piecewise function. We could think about what happens to the left of 0 and then what happens to the right of 0. So to the right of 0, this function looks like the line y equals x. To the left of 0, it looks like the line y equals negative x. Suppose I asked you about the behavior at 0. We could take the limit as x approaches 0 from the left. So as I approach 0 from the left, my y values are getting close to 0. We could look at the limit as x approaches 0 from the right. And if I look at coming in from the right, I would end up getting 0. And that means that the limit as x approaches 0 of f of x exists, and it is 0. So let's look at another problem. Let's look at this one. This function is a little bit more interesting. If we were to graph that in our calculator, we're going to go to y equals. We can type in absolute value. There's my numerator. Absolute value hits second and catalog 0. There's our absolute value. And we're going to see two lines here, but this is not a continuous function. So if you look at this, you see this line here, and then it jumps up here. So I'm going to draw just a sketch of that back on my notes. And then over at 2, it does the same thing. Let's talk about the behavior as we get close to 2. So we're going to find the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and then the limit as x approaches 2. So as I approach 2 from the left, we can see that we're getting close to that y value of -1. And as I approach 2 from the right, we are getting close to that y value of +1. But notice the left hand and the right hand limits aren't matching up, which means the limit at 2 does not exist. So now I want to jump a couple of pages into the notes and look at just a couple more examples. So here's 2 more piecewise functions, and they're asking us some questions here. Let's answer a few of these. Let's start with number 10. 10's asking us to use this figure and find f of -1.5. So that's just asking what's the y value. So at -1.5, which would be about right here, that y value would be 2. If we look at maybe this one, f of 1.25, 1.25 would be about here. So we could estimate that y value, probably about 1.75-ish would be a good approximation for that. Now let's jump in and look at some of the limits. Let's look at 13. 13's asking us to analyze what's happening as we approach 0 from the left. So here's x equals 0. As I come in from the left, I'm getting close to that y value of 2. So we would say that limit is 2. As I approach 0 from the right, we would also say we are getting close to the y value of 2. So notice my left and my right hand limits are matching, and they're both going to the same place, which means my limit at 0 exists, and it's 2. And then in this case, if we find f of 0, that y value when x is 0 is 2 using that graph. Now let's take a look at 14. Well, instead of 14, let's look at 15. That's more interesting. 15 is looking at what's happening when we get close to 2. So as we get close to 2, I'm coming in from the left. My y values are getting close to 1. But if I come in at 2 from the right, here's my 2. My y value is now at 2. So notice my left hand limit is at 1. My right hand limit is at something different, which is 2. This limit does not exist. The left hand limits and right hand limits are going to different places, so the limit at 2 doesn't exist. And then they're asking us for f of 2. F of 2 is defined right here where we have that solid dot, and that y value at 2 is 2. So f of 2 exists in this case, but that limit does not exist. E is asking us, is it possible to redefine that function so that the limit as x approaches 2 of f of x is equal to f of 2? And when we talk about redefining functions, we want to redefine, if we can redefine, it's got to be something simple. It's easy for us to plug in holes, but we can't fill in big gaps. So notice this one, we have a big gap here. We can't fill that in. So I'm going to say no, it's not going to be possible for us to fix this, if you will, so that the limit as x approaches 2 is equal to what the function is at 2, just because there's a big gap there. There's an infinite number of points in between those values, and it's just not easy to fill in an infinite number of points. Now, if we look at this next problem over here, let's look at 23. So now I've got a different piecewise function. And I'm asking what the limit is as x approaches 3. So as x approaches 3, that limit is going to be equal to 1. And that's from the left. Now if I come in from the right and I get close to 3, notice that y value is also equal to 1. Because the left and the right hand limits match up and they're going to the same place, then we have the limit exist at 3 and that limit is equal to 1. But if we were to look at what is g of 3, notice there's a hole here in that line that we were using, but it is defined up here because of that solid dot. So that y value is 3 for this. E is asking us, is it possible for us to redefine g of 3 so that the limit as x approaches 3 is equal to g of 3? So they're asking, is there a way to make this equal to this? Well, in this case, it would be easy to do so because we could just move that single point and fill it in right there. If that point was the only issue, just one single point. And a single point is easy to redefine. It's different than the last problem because in that last problem we had a gap. And gaps are not easier to redefine. So in this case, yes, it's definitely possible for us to redefine that one single point so that that limit is equal to the value of the function at that value.